Okay.
Hello, this is Mr. Shana. Okay, we're going to learn about conservation of momentum in two dimensions. Conservation of momentum in two dimensions. Tell me, when I had kinematics in two dimensions, when I had things flying through the air at weird angles, how did we deal with that? Say that again, Izina?
X and Y components.
Yeah, we did X and Y components. We treated the X and Y directions totally separately. And then when we moved on to Newton's second law of motion, and when we did free body diagrams and F equals ma, and I had forces acting in weird directions, then what did we do?
X and Y.
X and Y components. Some of the forces in the X direction equals max, some of the forces in the Y direction equals may. Well, now here we are with momentum. And we're going to have conservation of momentum in two dimensions. And how do you suppose we're going to deal with that?
X and Y.
If you think in X and Y directions, you are correct. We're going to be doing conservation of momentum in the X direction, right? The initial momentum in the X direction equals the final momentum in the X direction. And we'll do conservation of momentum in the Y direction. The initial momentum in the Y direction equals the final momentum in the Y direction. Great. That's the way we're going to do it. You guys ready to go? Good. Here it comes. I've got this puck here. We'll say it's a 3-kilogram puck. And we'll say it's going 4 meters per second that way. And I've got this puck here, and we'll say it's a, I don't know, a 5 I'm totally making up these numbers right now. 5-kilogram puck, and we'll say it's going 2 meters per second in that direction. You guys okay with that? Great. And now these two pucks are going to go until they slam into each other, and it will be a completely inelastic collision where this 3-kilogram puck and this 5-kilogram puck are now stuck together, and they will go off in that direction at some velocity v. And my goal is to find v. Find v, both magnitude and direction. You guys okay with that? Well, you know what I'm going to do next. I got to get the X and Y components, correct? So if this is V, I'm going to call the X component of V, Vx, and I'll call the Y component Vy. What I'll do is do conservation of momentum in the X direction to find what Vx is, do conservation of momentum in the Y direction to find Vy, and then I'll do Pythagorean theorem to find V, and I'll do inverse tangent to find what this angle theta is. You guys okay with that? Alrighty, let's let her rip. Initial momentum in the X direction equals final momentum in the X direction. Give me a number. What's my initial momentum in the X direction? What do you guys think? Give me a number. Nicole is, Noelle. You have two first names.
Yes,
that
I
messes
know.
me up. Noelle is
I answered
mouthing.
to both.
She's mouthing the number 12. How many people agree with her? Yay, yay for each and every one of you. My initial momentum in the X direction is only 12. This guy is not making any contribution to the momentum in the X direction, only that guy. So I got 3 kilograms times 4 meters per second. And then my final momentum in the X direction, these two guys are stuck together, right? To make a grand total of 8 kilograms times the final velocity in the X direction. Or I guess I'll just call it Vx. And so I got, what is that, 12 over 8? What's 12 over 8? 1.5? Yay. I'm halfway there. I'd like everyone to please get me the final velocity in the Y direction. Please do that now. I'll give you like a minute. Get me Vy.
Mr. Shana, why is your internet so slow?
Because of Russian hackers. I know, I just hate them. They're so Russian and communistic. Here, I'll get you started. Initial momentum in the y direction equals final momentum in the y direction. There you go. You guys do the rest. So you guys got an answer? Tell me, Chris, what'd you get?
1.25.
Chris says 1.25. I'm going to agree with him. So do I. Let's go for it. Initial momentum in the y direction is the 5 kilograms times 2 meters per second. The final momentum in the y direction is the 8 kilogram mass multiplied by Vy. So I get 1.25 meters per second equals Vy. Yay. Now I can go ahead and answer the question. I can get V and I can get the angle. The magnitude of V is going to be the square root of 1.5 squared plus 1.25 squared, which ends up being 1.95. And the angle theta is going to be the inverse tangent of the Vy over Vx. So it'll be 1.25 over 1.5. Which is about 40 degrees. And there we go. Any questions or issues on this? 2 dimensions, baby. Just do conservation momentum in the x direction and conservation momentum in the y direction. Well, here comes one you guys get to do. Here comes example number 2. I have a coal chute with a lump of coal on it. This lump of coal is going 8 meters per second. It's a 25 kilogram lump of coal. And it's coming down a coal chute that's at a 60-degree angle with the horizontal. That lump of coal is making its way to a coal cart. This lump of coal is going to hit the coal cart, which by the way is 50 kilograms and it's at rest. And then the lump of coal in the cart will go on their merry way to the right. I want you to find the speed of the cart plus coal after the collision. Someone explain to me, how am I going to do this? Is anyone thinking conservation of momentum? Hope so. But tell me, what's the only direction I'm really interested in? Noel, why, Logan, why do you say the X?
X direction because
Yeah, go ahead.
it's
All right, why the X direction? Yeah, Alexis.
because the cart's going to move on the left.
Yeah, because that's the direction it's going. Sure, absolutely. By the way, conservation of momentum in the y direction, I've got the coal, I've got the cart, but what other mass would I have to include if I wanted to do conservation of momentum in the y direction? Is anyone thinking the mass of the entire planet Earth? Right? It's going to slam into the cart, and now you're colliding. This 25 kilogram is colliding with the cart and Earth. So it's really not going to have much effect in the y direction. So all we care about is the x direction. So please do, here, I'll even get you started. Initial momentum in the x direction equals final momentum in the x direction, which means I'm not going to be using 8, no siree. What am I going to have to use for my velocity? How about the x component of the velocity? So I need everyone to please get the x component of your coal's velocity, because that's all that's going to matter. Okay, good luck. Get the x component of the coal's velocity, get the initial momentum in the x direction and the final momentum in the x direction, and find the speed at which the cart and coal go. after the please you. I'm gonna walk around and quote unquote help you. Oh shoot, is that, is that the, okay, yeah, what is it? Yeah, intro to the differential equations. Let's see what we got going on here. Okay, good. See your correct answer in your future. All right, good for you. Well, that's fine, then you'll get 1/4 of what everyone else gets. Yeah, you did it wrong. You saw it too, huh? Well, my 8s sometimes look like 2s.
I think it's also because like the line.
Oh yeah, good for you. Ooh, buddy, yay. Okay, great. That's an 8. Yay. Ooh, I'm in this part of the classroom. Yay. Yay. What is that?
That's a 2, right?
No, it's an 8.
Oh.
Ah, you're fine then. But it's an 8. Okay, Gavin's doing his thing. Okay, Jasmine, what do you have as the, I mean, I'm so sorry, Pooja? Jasmine sits there in another, no, near there. Look at the left side. What are you getting as the initial velocity in the x direction? Oh wait, you have the initial, yeah, well, no, the initial velocity in the x direction should be 4. If it's going down the chute at 8, then the x component is 4. So, and the coal is 25. The coal by itself is 25 kilograms, not 50.
What the heck?
Like on paper or on paper? Basically. I'm serious.
You need.
Good job. Oh yay, oh we're so smart over here. Good job. Man, I gotta get these chairs to be harder and lighter.
Well, I guess we either both get in or we I didn't mention it. No, I mentioned it, but I didn't want to say the name.
Yeah, I need to move these chairs away from each other. Alrighty. First of all, sometimes my 8s look like 2s because this guy here isn't dark enough. That's an 8. Alrighty, and so because this is a 60-degree angle, this is going to be 4 meters per second. The x component is 4 meters per second. And so you end up with 25 kilograms times 4 meters per second equals 25 kilograms plus 50 kilograms times v. And so you get 4/3 meters per second equals v. You guys okay with that? Okay, then hey, there's one last thing. I mean, this is all there is to conservation of momentum in 2 dimensions. Just split it up into the x and y directions. I need to show you one more type of problem that requires one little mathematical trick. And it's going to be a problem like number 32. So essentially, I'm going to do this problem for you, and then your practice of it will be to do problem 32. Here we go, a problem like number 32. I got A, and I got B. A is, let's say A is 4 kilograms, and B is 3 kilograms. Alrighty? A is going 5 meters per second towards B, and B is at rest. And then, bam, they hit, but it's not a completely inelastic collision like before. It's going to be somewhat inelastic, and A is going to fly off at a 42-degree angle. So here's A going off in this direction, V sub A, and B is going to fly off at a 55-degree angle. And so here's VB, the speed at which B flies off. You guys okay with that? It's like 2 billiard balls, only of different masses. They collide, and this guy goes off in that direction, and this guy goes off in that direction. And your job is to find VA and VB. Now, if we do this problem, like example number 1 earlier this period, I would just put VAX and VAY and VBX and VBY. You know what I mean? I would do this. I'd say, okay, I'll get the X component, VAX, and the Y component, VAY, and then I can do Pythagorean theorem and inverse tangent. Well, I don't need to do inverse tangent. I can do Pythagorean theorem and I find VA. And I can do the same thing here. Get VBX and get VBY. There's only one problem. I only have 2 equations. I have conservation of momentum in the x direction, and I have conservation of momentum in the y direction. 2 equations. But if I do it this way, I have 4 unknowns. So doing it this way isn't going to work for me. But there was an alternate way to get components, something we've seen in previous problems involving force. And it's to express these guys as the product of VA times something. Look at this. Instead of calling this VAX, I know that this is a 42-degree angle, correct? So instead of calling it VAX, I can call it VA times what? Yeah, cosine 42. And that's the trick. That's the big trick you're going to have to do. You can't call it VAX and VAY. You're going to have to call it VA cosine 42. And this guy is VA sine 42. You see? You're going to have to get the x and y components in terms of one variable. This guy isn't VBX. It's going to be VB times the cosine of 55 degrees. And this guy's going to be VB times the sine of 55 degrees. So sometimes you can get away with that XY stuff, but other times you can't. So now I'm going to start doing conservation of momentum in the x and y directions. And you'll see how to do this. Let's do conservation of momentum in the x direction. Initially in the x direction, all I got is this guy. This guy's making no contribution to the momentum. So I got 4 kilograms times 5 meters per second. The final momentum in the x direction, I got this guy going at this speed, and I got this guy going at that speed. So I'm going to have 4 kilograms going at a speed VA cosine 42, plus this guy, which is 3 kilograms, going at VB cosine of 55 degrees. At this point, I'm going to multiply numbers to make my life easier. So this ends up being 20. This here, I got 4 cosine 42, 2.97. 2.97 VA. 3 times cosine 55, 1.72. There's one equation with 2 unknowns. And I'm going to do the same thing with conservation of momentum in the y direction. My initial momentum in the y direction is 0. Neither of these balls or pucks or whatever are moving in the y direction. So their initial momentum is 0. After the collision, I got the 4 kilogram puck moving at the VA sine of 42 degrees. And I got the 3 kilogram puck moving at VB sine 55. Except for one thing. Do you notice that this puck is moving up, so he's got a positive momentum? This puck's moving down, so he has a negative momentum. But I want my VAs and my VBs to all be positive. So that means in this equation, I'm going to have to make it negative. I'm going to have to say, hey, I've got a positive momentum and a negative momentum. So I got the 4 sine 42, 2.68 VA minus 3 sine 55, 2.46 VB. Three hours? Why is my internet so slow? Me neither, man. Maybe there's some teacher here like downloading some huge game or something. Okay, I have 2 equations with 2 unknowns, so I'm going to have to solve them. And I'm going to use substitution method. Many of you are absolutely horrible at algebra, so I'm going to actually show this to you. I'm going to solve for VB. So I'm going to add 2.46 VB to both sides and then divide both sides of the equation by 2.46. So I get 2.68 divided by 2.46. And I get 1.09 VA. Okay? Now that I have that relationship, I can substitute that in here. So I get 20 equals 2.97 VA plus 1.72 times, instead of VB, I'm going to substitute 1.09 VA. Now I have one equation with one unknown. So the next thing I'm going to do is add like terms and then divide both sides by the coefficient. And I got 4.13. And now that I have VA, I can find VB. Alrighty. So hey, that's how you do problem 32. I just want to remind you again, make a drawing so that it's really obvious to you. Label your speeds not VAX and VAY, but VA cosine of the angle, VA sine the angle. And then do conservation of momentum in the X and Y directions. And I would recommend substitution method. I think that's a lot easier than trying to do linear combination. I mean, I'm going to try to find some way to add these 2 equations together and have the V sub a's cancel out. That's going to be just a huge hassle. Just do substitution method. Okay, any questions or problems on that? Here, I'll get in the camera. We're done.